Now we're going to talk about linear transformations. Some but not all of what I talk about today can be found in section 2.6. So really the subject here is more about abstract vector spaces. So let's recall what that was about. Remember we've talked a lot about Rn, which is the vector space of all n tuples x1 through xn. And then we abstracted this and had the notion of an abstract vector space in section 2.1, which is a place where we have vectors and we can add vectors and multiply them by scalars and so on. And we have the concept of a basis of a vector space. In Rn, we have the usual basis, which we label E1 through En, where Ei is the vector with a 1 in the ith place. And remember, the property that this has is any vector in Rn can be written as a linear combination of these basis vectors. The vector x1 through xn is this linear combination, and that's unique. There's only one way to do that. And that led us to the concept of a basis of an abstract vector space. If you have any vector space, what a basis is it's a set of vectors v1 through vn. First of all, these vectors are required to be linearly independent. And second of all, we asked that they span the entire vector space. If they satisfy that, then it's a basis. And if you have any vector in a vector space, it can be written as a linear combination of the vectors in the basis. That's the span condition. And the coefficients a1 through an are uniquely determined. That's the linear independence condition. So just to warm up and remind ourselves, let's look at an example. Take R3 and take the subspace of R3 given by the vectors x, y, z, whose the sum of the coordinates is 0. Remember, a subspace of a vector space is a vector space in its own right. In this case, it's two-dimensional, and for a basis, we can take these two vectors. And then any vector in this subspace can be written as, well, let's see, y is necessarily minus x minus z. So if you replace y with minus x minus z, we see that this vector can be written as x times the first basis vector minus z times the second. So this is a two-dimensional vector space, and I've chosen a basis for it here. Okay, now that's a summary of what we've already done, and now here's the new thing. Let's talk about maps between vector spaces. So let's look at an example. Let's just look at maps between from R2 to R2. Well, so that's a map from xy, and let's use uv for the coordinates in the target space. Well, here's a totally random function. Take xy to x squared plus 2y, sine of x minus cosine of y. And that's u and that's v. So basically you can take any function u of x and y and v of x and y. But we've talked a lot about functions which look like this, 2x plus y, 3x minus 4y. In other words, a function given by a matrix. In this case, the matrix is 2, 1, 3, minus 4. And that's a very special and simple kind of function. And the general thing is a 2 by 2 matrix, which gives you a map from R2 to R2. Or more generally, an m by n matrix gives you a map from Rn to Rm. And what is special about these? How do you say what's important and different about maps between vector spaces between Rm and Rn, which are given by a matrix? So let's look at a very simple example. Suppose you look at maps from R to R. So we just have a function of x. Well, for example, you could have the function x squared plus 1, or 2x plus 3, or 3x, and so on. Well, there's only one kind of these, which is given by a matrix, that is to say, multiplying by a constant. That's a linear function. F of x plus y is f of x plus f of y. Because, of course, 3x plus y is 3x plus 3y. Okay. Just for contrast, the function 3x plus 1 is not linear. You're not allowed to have a constant term because f of x plus y is not equal to f of x plus f of y, because the right-hand side is 3x plus 1 plus 3x plus 1, and you get 3x plus y, which looks good, but the constant term doesn't work. You get, on one side you get 2, and the other side you get 1. Okay, well, we already talked about all of that a few weeks ago. That was just a reminder, but now we're going to abstract it and talk about it in the context of an abstract vector space. So suppose we have a map between two vector spaces, f mapping v to w. We say that f is a linear transformation, or we'll sometimes say that f is linear for shorthand, if the following two conditions hold. Well, first of all, f of v plus w, or excuse me, v1 plus v2 is required to be f of v1 plus f of v2, where v1 and v2 are in v. And secondly, f of c times v is required to be c f of v. So these are exactly the same conditions that we had when we talked about linear transformations from Rm to Rn, but now we're just saying them in the context of an abstract vector space. And so, for example, if you have a linear transformation from R2 to R2, well, f of 1, 0 is some vector. So, I don't know, let's call that vector AB. And similarly, f of 0, 1 has to be something, and suppose that's CD. Well, the important thing is that just that information completely determines the linear transformation. That is to say, how do we figure out what f of xy is? Well, f of xy is, we can write xy as x times 1, 0 plus y times 0, 1. And by the fact that f is linear, we can break it out like this: x times f1, 0 plus y times f of 0, 1. And we know that f of 1, 0 is, let's see, AB, and f of 0, 1 is CD. And so that tells us what the value is at an arbitrary vector. It's this. In other words, it's written as a matrix like this. So again, this is more or less something that we've seen before, but I'm saying it this way to, well, to refresh your memory, and also to emphasize that the whole thing can be done, again, in a more abstract setting. So in other words, the conclusion is a linear transformation from Rn to Rm is given by a matrix, an m by n matrix. So, let's state that as a theorem. A linear transformation from Rn to Rm is given by an m by n matrix as follows. Well, you see what t of the first basis vector is, and, well, it's some vector a1, 1 through a1n. And suppose that t of 0, 1, the second basis vector, has some coordinates a2, 1 through a2m, and so on, all the way down to the t applied to the last basis vector, and we write that like this. And then the matrix of this linear transformation is you take these aijs, and you put them in a matrix as follows. And this is an m by n matrix. So, how do we say that for an abstract vector space? we have a map from one vector space V to another one W. How do I think of it in terms of a matrix? Well, the key point is I need to have bases around. So let's pick a basis V1 through Vn of V and W1 through Wm of W. And then just as before, T of V1 is some linear combination of the Wi's. Let's write it this way. And T of V2 is, again, some linear combination of the Wi's. So we'll call those coefficients the A2's and so on. Up all the way down to Vn is some linear combination. And we get a matrix. Just as before, the matrix looks like this. You put the aij's into an m by n matrix, just as before. So let's state this formally. So I'll state it as a theorem. Suppose T is a linear transformation from V to W. We often like to use T to remind you that it's a transformation, a linear transformation. And suppose the dimension of V is n and W is m dimensional. And now the key point is you have to pick bases of these two vector spaces. And so you pick a basis of the first one, V1 through Vn, and a basis W1 through Wm of the second vector space. And once you've done that, then the linear transformations from V to W are given by the n by n matrices. And the way you find a matrix corresponding to your given linear transformation, I'll write it this way, is you fill in the columns like this, and the key point is that the ith column of the matrix, which I'm circling here, is the coordinates of T applied to the ith basis vector, which is to say T of Vi is this given linear combination of the Wj's. And every linear transformation is given by a matrix, and every matrix gives a linear transformation. And it's important to note that the matrix that you get depends on the basis. Of course, it doesn't even mean anything to write down a matrix without a basis in mind. So let's look at an example of that. Suppose I had a vector space V with a basis V1, 2, and 3, and W a two-dimensional vector space. And suppose that I told you that T of V1 was W1, and T of V2 was W2, and T of V3 was W1 plus W2. Well, then the matrix of this linear transformation looks like this. 1, 0 is the first column, and 0, 1 is the second, and 1, 1 is the third. That is to say, T of 1, 0, 0 is 1, 0. And T of 0, 1, 0 is 0, 1. And finally, T of 0, 0, 1 is 1, 1. So that's just the three defining relations of T that I gave there in matrix form. Okay, that's fine. But what happens if we chose a different basis? I want to see how T changes. So suppose I chose a new basis, U1, where U1 and U2 were V1 plus V2 and V1 minus V2, and then I just chose U3 to be V3. So in other words, I changed the basis of V, but let's leave the basis of W the same. What effect does that have on the matrix? Well, let's see. What is T of U1? Well, U1 is V1 plus V2, and therefore I calculate it as W1 plus W2, and similarly T of U2 is W1 minus W2, and T of U3, well, that's just the same as T of V3. That's what it was before, W1 plus W2. And so with respect to this basis, I get the matrix, well, the W1 plus W2 gives me a 1, 1 in the first column, and the W1 minus W2 gives me a 1 minus 1 in the second, and finally we get a 1, 1 in the third. So it's important to realize, to be careful what's going on here. This is the same linear transformation. In one basis it has this matrix, and in the other it has this. But so it's the same linear transformation, but its matrix, you get two different matrices depending on the basis that you choose. Okay, so there's an important consequence of all of this, and in some sense this is one of the main reasons I'm talking about all of this, and it's the following. Every vector space is essentially Rn. And this is an important concept. I'm going to emphasize it here. What do I mean by that, essentially Rn? Well, the point is that the concept of a linear transformation makes this clear and precise. So suppose I have a vector space V. I can choose a basis of it. So let's say V1 through Vn. And now take the usual vector space Rn with its standard basis E1 through En, where as usual Ei is the basis, is the vector with an I in the with the 1 in the ith place. So I'm going to define a linear transformation from my vector space to Rn. Well, simply define it to take Vi to Ei. I'm allowed to do that. To give a linear transformation between two vector spaces, it's enough to tell you what it is on the basis. And it's clear that T is a one-to-one and onto map from V to Rn. So it sort of identifies V with Rn. You identify Vi with Ei by the linear transformation T. And there's a linear transformation T inverse going in the other direction, just taking Ei to Vi. And so what this says is that for all intents and purposes, this vector space really can be thought of as Rn. It's in bijection with it. You can identify it in an elementary way. Okay, this is sufficiently important that I want to say it as a theorem. Suppose V is a vector space and its dimension is n. Let's choose a basis V1 through Vn of this vector space. Then there is a one-to-one onto linear map or linear transformation T mapping V to Rn. And it's determined by saying that Vi goes to Ei. And we say that V is isomorphic to Rn. And that's just a fancy way of saying that we can really think of V as being Rn. So that's what I mean by saying that every vector space, so to speak, is Rn. But it's really important to keep in mind that when we identify it, the identification of this vector space with Rn depends on the choice of basis of V. Okay, let's look at an example of all of this. Go back to the example way back at the beginning of today's video. Let's take this vector space V consisting of the vectors in R3 whose coordinates add up to 0. This has a basis V1 and V2 as indicated. So this is a two-dimensional vector space. So I'm claiming that we can think of this V as being R2. And the way we think of it is we map the vector 1, minus 1, 0 to 1, 0 and 0, 1, minus 1 to 0, 1. That is to say V1 goes to E1 and V2 goes to E2. So where does XYZ go? Well, XYZ is X times this basis vector plus, minus Z times 0, 1, minus 1. And so, according to the properties of linear transformation, the map takes XYZ to the two-tuple X minus Z. So this is an identification of this two-dimensional vector space with R2. It maps the vector xyz, provided the coordinates add up to 0, to the vector x minus z. And this is a one-to-one and onto map. So I'm just going to say sort of vaguely the conclusion of all of this, but this is quite important. Everything we've been talking about, Rn, matrices, determinants, Gaussian elimination, row echelon form, and everything we're going to be talking about in the rest of the semester carries over entirely to the setting of an abstract vector space, to any n-dimensional vector space. And the only caveat is that the details of how that happens depends on the choice of the vector space. But the sort of big picture, how everything works, is exactly the same. And we're going to be talking quite a bit more about this as we go through the rest of the course, and this is kind of an introduction to all of that.